Welcome everyone to the IUSSP panel roundtable on digital demography. Today we will discuss highlights and future directions. My name is Emilio Zagani and I will serve as chair and moderator of this session. I'm also chair of the IUSSP scientific panel on digital demography, which is the group that is sponsoring this event. If you want to know a little bit more about the activities of the panel, I'm going to put the link into the chat so that you can see recent activities of the panel. Now, today we are extremely lucky to have 4 interdisciplinary leaders who will provide input presentations on the use of digital trace data for population research, as well as on the implications of digitalization for inequalities and population outcomes. Each of the speakers will give a short talk on exciting projects they're working on. And then we will move to the general discussion. Please use the chat to write your questions or comments for the speakers as we go along. The question can be either specific to the presentations or there could be broader comments on challenges, opportunities, and future directions for digital demography. After the 4 talks, then we will open the panel for a broad set of conversations with Q&A, and I will draw from the questions that you have posted in the chat. Now, one maybe practical aspect, I don't know the circumstances in which you are at the moment, but if you would like to, you can turn on the camera. That might sort of make it a little bit more personal for interaction and so on. Some of you may or may not be able to do so, but if you want to do so, I would invite you to participate with the camera on, if that is possible at all. Now, without further ado, let's get started. The first speaker for this session is Andy Tatum. Andy Tatum is professor of spatial demography and epidemiology at the University of Southampton, and he is director of WordPop and FlowMinder. He is interested in how populations, their characteristics, and their dynamics can be mapped at high resolution across low and middle income countries. His research has led to pioneering approaches to the use and integration of satellite, survey, cell phone, and census data to map the distributions of vulnerable populations for disease, disaster, and development applications. So we are very excited to have Andy. Andy will be talking about estimating small area population distributions, demographics, and dynamics through geospatial integration. So Andy, the floor is yours.
Thank you, Emilio, and yeah, thank you for spending your time to join this session. So in my, I think, 12 minutes we have, I'm going to give an overview of some of the work going on in our group and other groups with trying to map populations, particularly using digital data sets. So, let's go to the next slide. So small area population data for mapping populations, it's got a huge amount of uses. It underlies so much of governance and so much, particularly recently with the control, the mitigation of COVID, with health system planning, modeling, meeting SDGs, health metrics. But we also face a challenge in many areas of the world. So this is Democratic Republic of Congo, about the size of Western Europe. We do have population estimates, you can see there on the right, high population, low population, but each one of those units is about the size of a small European country. And the major problem, of course, is the last census was 1984. So those estimates are projections made using a variety of sources. And what we end up with is often we talk to one ministry who say there are 60 million people in the country, and you go to a different ministry, there are 100 million people in the country. So it's a major challenge, and it's not unique to DR Congo. If we look at the last census date for a set of countries here, for some it can be decades. But it's not just that kind of situation. There are lack of registry administrative data sources to keep census counts up to date. And COVID has disrupted the plans for many countries to conduct a new census in the 2020 round. And even with a reliable census, as soon as that census has been done and the people have been counted, there are high spatially varying fertility rates that can change those distributions of populations. There, of course, is migration, and there is displacement in some of the most conflict and disaster affected areas, all of which make population data outdated pretty rapidly, particularly at small area scales. And this is challenges that we often face and National Statistics Offices face, and those can come from course resolution. The data can be outdated, it can be incomplete and inaccurate. And we're often looking at scenarios like this, where maybe there is a complete coverage, but it's a projection from a long time ago, or there is recent data collection, but it's been, there are gaps in it. Maybe there are in the small areas where data could not be collected due to conflict, or there's an entire country that hasn't been enumerated for a long time. So we have digital data sources that we can start to make use of. So here's a satellite image of a rural area in Afghanistan. With our eyes, we can pick out where the rural settlements are to help us get an idea of where the people are and are not. Nowadays, there are complex algorithms, sophisticated methods to extract in a fraction of a second the buildings. And this is something that's being done more and more. It's not perfect, but we have now maps of the entire Africa taken from recent satellite imagery and extracted from those the building footprints. It's not only building footprints, we have images of the earth at night, vegetation amounts, topography, we have land cover, and the mapping of settlements at fine spatial scales than we've ever had before. And of course, the mapping of road networks, points of interest as well. Just this a wealth of digital data sets that describe the landscape. And not only that static landscape, but something about the dynamics as well. So we may hear later as well from speakers about the use of mobile phone data, particularly from internet tech giants and the movement of smartphones, or from collaborations with mobile network companies themselves. So the movement and registry of every time you make a call or receive a text message, the digital breadcrumbs we leave behind, and the aggregated anonymized data that can come from those to measure population movements. So what we do at WorldPop and many other groups do is try and integrate and make the use of some of these types of data to get the strengths of each to fill in some of the gaps and weaknesses that exist. So those can come from traditional data sets, counts, census counts matched to boundaries, household surveys and their cluster locations, the locations of villages, road networks, mobility patterns, and satellite-derived data sets on things like building footprints. And what's being developed across different groups is types of models to address these different scenarios. And I'll talk about these top-down and bottom-up types of models to try and estimate populations at small spatial scales. The top-down approach, where we have a complete enumeration from a census or from projections, and we're using that finer spatial scale data to disaggregate to grid square estimates. And here's an example here from northern Vietnam. Maybe we have counts at the district level, but we don't know where the people are within those locations. But in our stack of data, we have information on satellites to tell us there are buildings here, so likely there are people here. It doesn't tell us anything about those densities, but maybe we have information on land cover that can tell us something about how population densities maybe vary by different region, or electrification, satellite night lights showing evidence of different types of densities. And when we bring together those stack of data, we can go from this aggregate picture to disaggregate those population counts to grid square levels. So this is something that ourselves, other groups have done across the world now, to take census projections, estimates at subnational, district level, at province level, and disaggregate those to grid squares using maps of building footprints, using geospatial data sets to learn those relationships and try and estimate where those populations are. And these kind of data sets are increasingly finding use in health information systems, in estimating populations at risk. But they face some major problems. Some of the widely used gridded data sets ourselves, our own global data sets at WorldPop, Landscan, GPW, are all based on projections in many countries from outdated census units and disaggregating those. So no matter how detailed the covariates or sophisticated the model is, we're often putting bad data in and getting bad data out. So how can we capture and quantify those uncertainties and produce better estimates? So this is where the recent years, and a lot needs to still be done in the research field, is focused on these bottom-up approaches. So how can, in the absence of a full enumeration, how can we estimate those populations in the gaps? And so instead of this top-down approach, we're making use of recent small area population counts to, in a similar way, use those geospatial covariates and predict into those unsampled areas. So we have population data, settlement data that feed into spatial statistical models to estimate populations numbers, ideally with uncertainty around those estimates. Why do we need geospatial covariates if we just have population counts and settlement mapped out? Here's an example from Pakistan. Two villages, they look identical pretty much from satellites. So why not just assume that there are, from household survey data, assume there are 10 people per compound and then just redistribute people and make a population map. Here's the problem: when we look at household survey data, we see in one area of the country, there's more than 11 people per compound. In another area, it's less than 5. So we need to start to account for those variations within cities, within regions across the country. And this is where these sets of digital data sets, geospatial data sets, come in to try and describe something about the landscape, mapping buildings, roads, markets, conflicts, or something that can come from survey data or satellite data. And this can be extracted, extracting extra information from some of these digital data sets, and not just mapping out where the buildings are, but what are their densities in areas, their counts, how are the neighborhood types in there. We can immediately, with our brains, see that there are different types of neighborhoods there. Can we develop automated ways to map those? And can we identify what typically non-residential buildings look like and train computer models to identify those to give us another extra useful layer for population mapping? So these all feed into these statistical models. I'm not going to have time to go into all of the details of this, but increasingly within WorldPop, we're making use of these Bayesian hierarchical models and developing those with national statistics offices. So an example here in Afghanistan, where only in recent years have these pink areas been enumerated, and the model was used to then produce predictions with uncertainty into those unsampled areas. So these are leaving out some of the districts and predicting those gives us a pretty good confidence, but not perfect. And so some of those areas have very high uncertainty in the estimates. But these were used by the former government of Afghanistan in multiple applications. In Colombia, to fill in gaps where census enumerators could not go, these digital approaches, Bayesian approaches to fill in those gaps. The same in Burkina Faso, to fill in gaps in areas of conflict, to produce a complete set of estimates that fed into the preliminary census published estimates. And where there's been no recent enumeration at all, working with field teams to collect extra enumeration data to train the model and produce those predictions. And those are forming the basis now of COVAX microplanning to work out how much vaccine is needed and where to distribute it. And in DRC, so moving beyond those 1984 estimates for the first time to come up with these estimates in collaboration with the stats office and field teams. And all of these estimates come with uncertainty. And one way of using that is trying to translate that into operational use. So if you want to be 90% sure you have enough vaccine to immunize 95% of all children under 5 years of age, we can provide a conservative estimate of that. But it's all come with problems still. So this data are biased. The sampling strategies may not lend themselves to this kind of modeling. There's a lot of heterogeneity in urban areas that's hard to capture without dense sampling. Validation methods, that's the best way to do that. Dealing with mismatches, we're using population data from different years versus the geospatial covariates. And of course, how to use and communicate uncertainty in the outputs is often a challenge, and getting those accepted when they conflict with official projections. And finally, I'm just going to touch on the fact these are all static estimates, and of course, people move around. So this is where potentially the mobile phone type data come in. So this is movement patterns across 5 years in Namibia of movement of phones. And we can develop models to try and translate density of phones into density of people and capture those population density changes. Again, this comes with a lot of uncertainties, but shows, I think, the directions that we can go with some of these data sources to complement traditional data sets. And where we don't have access to phone data, there are potential for other sources. So this is satellite images of the Earth at night and the fluctuations we see as seasonal migrants move into different parts of cities, turn on lights, light fires. So some of the recent work we focused on is trying to bring together the strengths of each of these types of data to capture seasonal mobility, whether that's vegetation capturing growing seasons, urban rural areas to capture the different types of mobility that exists, working with phone operators to look at the movement of phones, mapping out when and how public and school holidays take place in different regions, and then bringing those together in a similar way in a multivariate Bayesian models to estimate changes from that baseline of population densities at subnatural scales. And of course, accounting for displacement where possible as well. So bringing those all together in this case for South Sudan to estimate those population numbers accounting for that displacement. And just finally, many challenges remain in getting towards all of this, capturing and quantifying these biases. Phones do not equal people. So how do we capture them and quantify those biases? Actually accessing the mobility data can be very hard to work with phone operators and phone data. And how do we harmonize all these different data sets that come at different spatial and temporal scales and been captured for different reasons? But ultimately, I'm hoping we can think about moving towards some kind of living census where we're complementing traditional data sets, maybe taking census counts, disaggregating those to grid squares, and in the intercensal period, working with administrative registry data, but also the satellite data, the mobile network data to complement that where gaps in space and time exist, and adjusting at all points where household surveys data come in, GIS feature data can be collected. So we can be in a better position when the next census comes along to have a baseline for preparing for that census and also adjusting those numbers. Thank you. I will stop there. My 12 minutes is up.
Thank you. Thank you very much, Andy, for this fascinating presentation. Just as a reminder for maybe those who sort of join midway, like we're not going to sort of address questions right now, but if you have questions in your mind that are fresh right now, please write them in the chat and then we'll have a general discussion at the end. Now we'll move straight to the second input that comes from Guanghua Chi. Guanghua Chi is a research scientist at Facebook. He has an interdisciplinary background that includes computer science, geography, and information sciences. Much of his research has been related to mining geospatial big data to better understand the interaction between social networks and migration, as well as to improve measurement of poverty. And today, it will be talking about micro estimates of wealth for all low and middle income countries. Guanghua, the floor is yours.
Thanks, Emilio. So my name is Guanghua. I'm a research scientist in the computational social science team at Meta. So my work focuses on the applications of machine learning on the development. So today I will present my work on using machine learning approaches to targeting humanitarian assistance by estimating the wealth. The collaborators include Han and Surao from Meta and my PhD advisor, Joshua Blumenstock from UC Berkeley. Just a little bit of context here. So for the past decades, lots of progress has been made on reducing the poverty, which is the first goal of the United Nations Sustainable Development Goals. So, but during the COVID-19, over 20 years, for the first time, the global extreme poverty is increasing. And according to the World Bank, the COVID-19 will add about 150 million extreme poor by 2021. Let me show you another concrete example because of this COVID-19. So our lab at UC Berkeley did a survey in about 15,000 households in Togo last July. One of the questions is, in the past week, how many days did you or someone in your household have to reduce the number of meals eaten in a day? If we focus on the last bar of this histogram, that means about 1/5 of the population in Togo have to skip one meal every day in a week. And if we focus on all the bars except the first one, that means at least half of the population in Togo have to skip one day in a week. So this histogram shows how serious the food crisis is because of COVID-19. And in response to the COVID-19, thousands of new humanitarian assistance programs were launched in the low and middle income countries. In each of those cases, the program administrators face the same problem, and it's a very hard decision on whom to prioritize to provide this assistance. The reasons is, one, they don't have enough money to help everyone, and two, they don't have a comprehensive data set about income or consumption of each household. So for instance, the latest census data in Somalia or Congo is about 30 years ago. And in those, unlike the rich countries like in the US, we have IRS, the poor people from the poor countries don't have a document to show how much they earn because they're working for if they have this informal work. So in this talk, I will talk about how we use machine learning approach to estimate the poverty so that we can help this humanitarian assistance. This is an overview of our approach. In figure A, that's the ground truth we used. It's from a nationally representative household survey from the Demographic and Household Survey in 56 countries, as shown in these green polygons. And figure B is Nigeria. It contains about 40,000 households in about 900 locations. Each location is 1 point in this map. And that's the ground truth we use. We also use lots of features like satellite imageries and other features. And then we combine the ground truth and the features to train a machine learning algorithm and then make the estimation of the poverty in the low and middle income countries. We do this model at a 2.4 kilometer resolution because most of our input is at this resolution. I will talk about the ground truth and features in detail in the following slides. So about the ground truth, that's from the Demographic and Household Survey. They do lots of surveys for each household, for thousands of households in each country. They design a relative wealth index. The way to calculate this index is about the collected 15 wealth-related questions, like the roof materials or the water resources, or whether this household has a TV. So using these wealth-related questions, they do a PCA and then take the first principal component and then normalize them. That's the relative wealth index. So we use this relative wealth index from DHS in 56 countries since 2000. That's our ground truth. In terms of features, Professor Tantum discussed lots of these features we use here, like satellite imageries. We use convolutional neural networks to generate features. We also use a nightlight imagery. Other features like geographical features, for example, road density or whether that area is urban or rural. And we also have use a population density data set. That's from the Facebook Data for Good product. It's a 30-meter resolution. And we also have connectivity features, which we found is a very important features based on the feature importance from the model, like the number of cell towers in that grid cell, 2.4 kilometer grid cell, or the number of Wi-Fi's. So we combine these features, we combine the ground truth and train a tree-based algorithm and then make the estimation. So our model has a pretty good performance. It can explain about 56% or 60% of variations of wealth based on the DHS survey, depending on the different cross-validation algorithms we use. So the basic cross-validation is the R-squared is 0.7. So basically say we train the model using 9 folds and then test the model using the left fold and then do it 10 times. But we know this is a spatial autocorrelation issue. So we use a spatial cross-validation and the R-squared is a little bit lower, it's a 0.56. But we think that's the right way to do. And for the figure B, that means most of these models are square. It's come from the ability to differentiate between the rural and urban. But within a rural or urban, our machine learning model can also distinguish this wealth index. And the figure C is some kind of other validations using independent ground truth. I will discuss it in details. So just to validate our model and to make sure or eliminate the possibility of the, that our model might overfit the DHS survey, we collected 4 independent ground truth and do this validation. So this is the first one from a census data in 15 low and middle income countries. The way we did this is try to aggregate the census data to the smallest administrative unit and then calculate this aggregated wealth index. So that's from census data. And it's the same for our estimations. And for the estimations, we also aggregate those grid cell to the same administrative unit and then compare their correlation. And on average, the R-squared in these 15 countries is about 0.86. So it's also quite accurate. And most importantly, these census data are never used by our machine learning model. So this is the validation at the administrative unit level. We also did another 3 validations at a very high spatial resolution. So it's in Togo, Nigeria, and Kenya. In 2018, Togo government did a nationally representative household survey in about 6,000 households. Nigeria, in the same year, Nigeria collaborated with World Bank, did about 20,000 household surveys. And in Kenya, an NGO called Give Directly did a survey in about 5,000 households. So we use this data, and one advantage of this data is not only they have this wealth index, they also have a very accurate location of each household. So we can do this high granular validation. We did this validation with our estimations. We also see a very high accuracy. For instance, excuse me, in Togo, R-square is 0.76 or 0.84, depending on the administrative unit level. And in Nigeria, it's also 0.5 or 0.7. And even in Kenya, this is a very small, like rural area. We can still distinguish this relative wealth or relative poor areas. And we make this data publicly available. And we also created this interactive map, so you can play with the data. And based on this validation, the Togo government and Give Directly, they use these estimations to find the poor in Togo. And then they distributed about $10 million to more than 100,000 households who are in poverty. So that's the applications of our estimations in the real world. And the data for good team at Meta has lots of other data sets. For instance, the Facebook population maps, the movement range maps, or displacement, and some social connective index. So that would be useful for other analysis. Okay, thank you.
Thank you, Guanghua, for this very interesting presentation. As I mentioned earlier, if you have questions that are fresh in your mind now or comments for general discussion, please feel free to put them in the chat, and I will draw from comments in the chat later on once we open it up to a general panel discussion. Now let's switch gear and move to our third speaker, Riddhi Kashyap. Riddhi is Associate Professor of Social Demography at Oxford University. She has broad interest in demography, including in how digital and computational innovations, both as a set of models, like agent-based models or microsimulation, and in terms of new types of data sources, like digital trace data, can contribute to social science. And she's going to give us an example related to the digital revolution and gender equality. Riddhi, the floor is yours.
Great, thanks very much, Emilio. Can I confirm that you can see my screen?
Yeah, that's all good.
Okay, great. Well, thank you very much for organizing this panel, and also to the other speakers. I'm really excited to speak in this very exciting group of interdisciplinary interests. As Emilio said, I'm Riddhi Kashyap, and I'm at the University of Oxford. And a lot of my research in recent years has been very much looking at the digital revolution and looking at both the impacts of the digital revolution in terms of the social and demographic impacts of the digital revolution. And the second part of my research in relation to the digital revolution has been thinking about the data implications of the digital revolution. So before I go further, I want to start off, of course, by explaining what I mean by the digital revolution. And the digital revolution here refers to the dramatic change in the technological landscape that's occurred roughly in the last 25 years. And you see this here on the slide, which shows technology subscriptions per capita at the global level from 1993 to 2017. And we see here significant expansion in essentially cellular or mobile technology, diffusion of mobile phones. And we also see, starting the mid-2000s, mobile internet, as well as the rise of fixed internet connections, right? And we see a kind of stagnation here of landlines. And this digital revolution is truly a global revolution. So we see this diffusion of mobile and internet technologies occurring everywhere in the world, in Africa, Asia, Europe, Middle East, North and South America, and Oceania. The levels of technology subscriptions per capita might be different, but the growth is the same everywhere. And in many parts of, for example, Africa, but also Asia, what's notable here is that the landline stage of telecommunication development was completely skipped. So really what we have here with the digital revolution is, with mobile technologies in particular, a real novelty in terms of telecommunication infrastructure in in these regions of the world. So, as I said, this is the starting point. This is the starting point. It provides the impetus for a lot of my research in the past few years, and it also provides the impetus for the sponsoring panel for this session, the panel on digital demography, because the digital revolution is first, as I said, a social revolution. And the question for demography and demographers is how and for whom are these digital technologies affecting demographic behaviors and outcomes. Digital technologies are crucial in how we access information, how we access vital services, how we communicate with each other. So a lot of the pathways to demographic outcomes are essentially now mediated in some way or another through access to digital technologies. So the first part of my presentation, I want to talk a bit about the work that I've done with collaborators looking at, in particular, the impacts of mobile phones in relation to sustainable development outcomes, especially linked to SDG 5 on gender equality. Then I'll come back in the latter part on the data revolution aspects, in particular in link to some of the work I've done using social media advertising data to study global gender gaps. So to start off with the digital revolution as social revolution, this slide here shows essentially the global correlation between mobile phone diffusion on the x-axis and on the y-axis, a range of different sustainable development outcomes. So first we have gender inequality index and contraceptive prevalence. So these are two indicators where we see this sort of strong negative correlation between mobile phone diffusion and reductions in gender inequality and contraceptive prevalence increase, positive correlation between contraceptive prevalence and mobile phone penetration. Now, these are essentially raw correlations for the time being, but in the paper, we actually do this with a country fixed effect specification, and we also have, we try a range of different other specifications. And one of the things that stand out when we also control for education, population density, economic development through GDP per capita is that there is a very strong association between these gender inequality index and contraceptive prevalence. And in the next slide, I show maternal mortality and under 5 mortality between these digital variables and these sustainable development outcomes. And what's also striking is that these effects or these associations are actually much more concentrated in the lowest and low income countries. So Q1 and Q2 in the quintiles of GDP per capita, right? So the larger associations in Q1, Q2 countries by GDP per capita. Similar patterns also in the mortality, in the correlations between mobile phone diffusion and the mortality indicators. So this is at the macro level. We see these associations, and we see these associations between the digital variable of mobile diffusion and these demographic and development outcomes are robust to a range of different controls in the macro level analysis. The individual level analysis, now Guanghe was already talking about the demographic and health surveys. Starting phase 7, the DHS includes also variables linked to mobile phone and internet access and internet use. And we see that this is here the first set of countries where these data from the digital variables become available. We see, of course, significant variation in women who have access to mobile phones in the DHS across the 7 countries in sub-Saharan Africa that are noted here. So we have 27% here in Burundi and 72%, for example, of women in the survey who had access to mobile phones. But we also see that when women do have access to mobile phones, they're using them for important things like for financial transactions and also in some cases for accessing information about family planning. Then we look at the individual level in these 7 countries and we look at the association between mobile phone ownership and a range of different outcomes surrounding decision-making on contraception, equality in decision-making in the household, sort of women's empowerment-linked measures that are classically quite well studied using the DHS, using modern contraception, knowing where to get an HIV test, as well as testing for HIV. And we see that there's actually, again, robust to a number of different controls. We find that there are strong associations between owning a mobile phone and accessing and women's empowerment and sexual and reproductive health outcomes. Now, of course, there are concerns about endogeneity. This is a cross-sectional survey, but actually through geospatial augmentation of the DHS, by merging it with geospatial data sets, such as, for example, lightning strikes, we harness a quasi-experimental strategy because places where lightning strikes occur more, cell phone towers are more likely to be disrupted and mobile connectivity is poorer. And we find when leveraging this quasi-experiment that actually these associations also hold up to the use of the IV and lead us to believe that these are plausibly causal correlations, plausibly causal associations that we're finding between the digital variable and the demographic outcomes that we're studying. We also find that the payoffs to technology are actually the largest in the sort of least developed microclusters in the DHS. And that's what we find in this heterogeneity analysis that we do, that the payoffs to phone ownership are actually largest in areas where local development measures, as proxied by night lights, another geospatial variable, is actually in some sense the lowest. So that's what I've talked about so far, the digital revolution and the social revolution, looking at the DHS. But in the latter part, I want to sort of give some examples of how we can also leverage new kinds of data sets, digital trace data sets, to also study gender gaps, as I've tried to do in my work. And a key data source here has been to harness the advertising infrastructure provided by social media platforms. And we can think of these advertising infrastructures provided by social media platforms as a type of digital census. So all social media companies, of course, have users, and of course the internet economy is based on targeted advertising. So the entire goal of, for example, companies such as Meta or Twitter and others is to provide information on its users to potential advertisers. And here I've, for example, queried using Facebook's Ads Manager. This is a bit of an outdated screenshot because it looks slightly different now. The audience size, the potential number of monthly active users in Nigeria who are men on Facebook, and this is 15 million people, right? So it's essentially a digital census of the Facebook population. Here for women, I can see that the potential audience is smaller, it's 9.1 million people. Similar audience estimates can be queried, for example, here for LinkedIn. We can look at audience sizes who are LinkedIn users by gender, by age, but also targeting criteria linked to industries, seniority, and so on, which is specific to this being a professional platform. So some of the applications in the work that I've done with collaborators in using these types of data sets has been to see to what extent can we expand the geographical coverage and also improve the temporal resolution of different types of SDG 5 relevant indicators on gender gaps using these social media digital censuses. So some examples of this is filling data gaps on internet and mobile access gender gaps, as you can see on our website, digitalgendergaps.org, where we use Facebook's ad estimates to generate Facebook gender gaps, which we find are highly correlated with ground truth survey data on internet and mobile access gender gaps. So we train a model using Facebook, for which Facebook is a very, very good feature to then expand geographical coverage of this. So this is just to give you an example. For example, here we have gender gaps in internet use from the best available surveys that you can find from the International Telecommunications Union. We see there are significant data gaps in this indicator in Sub-Saharan Africa as well as in South Asia. This is a female-to-male ratio of internet use as available from the survey data. So we see, again, data gaps. And then by training a model with the Facebook gender gap, we find that we can actually fill in, when we use Facebook gender gaps as a predictor, we can fill in these data gaps and get a model-based estimate of digital gender gaps for other parts with much better geographical coverage. So we see, for example, there are significant digital gender gaps disfavoring women in Sub-Saharan Africa and South Asia, as we can infer from this. Another extension that we're working on here is to see if we can do this also subnationally. And here we're using the DHS as ground truth and trying to expand coverage of digital gender gap indicators at the subnational level. And we find this is here Facebook gender gaps, we find that actually Facebook at the subnational level provides reasonably good coverage with the exception of in Sudan. And of course, the gray areas here are the areas where we have sparsity in that there are fewer than 1,000 women as noted by Facebook on its ad platform. We can do similar things with LinkedIn. So this is the LinkedIn Gender Gap Index, again, a female to male ratio of LinkedIn users. And we see that there are larger gaps disfavoring women in South Asia, Sub-Saharan Africa. Interestingly, in many of the formerly post-Soviet countries, we actually find, or formerly Soviet countries, we find actually there are many more women on LinkedIn than men, but that we also see that in the ground truth in the ILO labor force survey, where actually professional gender gaps there are actually in excess of 1 in places like, for example, Latvia or Lithuania. There are also interesting selection and bias issues that we can explore or that we have explored. For example, places where online gender gaps, we generally find that where there are larger gender gaps disfavoring women, online gender gaps actually show better performance for predicting these different gender gap indicators. But we also see that where there are places where gender inequalities are larger, there are nonetheless interesting biases that are visible. So an example of this is when we look at LinkedIn, in countries where women are less likely to be online, this is these green countries, this is the Digital Gender Gap Index, so these green countries where women are less likely to be online, the LinkedIn gender gaps actually lead us to be more optimistic about professional gender equality than is actually the case, which suggests that women who are online are much more selective in these places where there are greater internet access gender inequalities. Lastly, just to illustrate a point about another strength of these kinds of data sources is that they can allow us to sort of analyze changes as they're occurring in high temporal frequency or temporal resolution. So for example, on digital gender gaps, we found that there were larger increases in Facebook use amongst women, especially in Europe, places like Italy, over the March, April lockdowns, COVID lockdowns. Right? So that's one kind of change that we're able to pick up by regularly querying these data sets. The second thing, here's another example, is that with the fall of Kabul recently in the summer in Afghanistan, we found very interesting patterns where the daily active use amongst adolescent women and girls in Afghanistan, particularly in this age group of 15 to 19, really increased. So Afghanistan, as you might recall from the digital gender gaps map I showed, is one where actually there is a significant, there are considerably fewer women than men on Facebook than for example, in Europe, but we actually saw increases in women, in girls and women in this 15 to 19-year-old age group using social media over this period, kind of change that we're able to pick up given the temporal resolution of these data streams. So just to summarize, the work that I've shown today is an example of how, from a demographic perspective, it's really important for us to think both of the social as well as the data implications of the digital revolution. And understanding the impacts of digitalization, I think, is vital now to understanding demographic and sustainable development dynamics. From a data perspective, I think harnessing the data revolution truly requires us to both use old as well as new sources of data and think of ways to link them in different ways within an increasingly diversifying data ecosystem. And I've also tried to make a point, as with the work with digital gender gaps, that demographic analysis of digital populations, looking at sort of age and gender variables on digital populations, is really interesting because in of itself to illuminate new types of population inequalities, but they can also help us understand biases and the generalizability of digital data streams in new and important ways. So that's all I have. Thank you very much. And I look forward to comments and the discussion in this session.
Thank you very much, Ridik, for this very interesting and relevant project that you shared with us. Let me also add my digital applause. Let's now move to the fourth speaker, the fourth and last speaker for this panel, Rumi Chunara. Rumi Chunara is Associate Professor of Biostatistics and Computer Science at New York University. She researches and develops ways to use unstructured data in real-world applications and to better understand population health. As a computer engineer and scientist, she has contributed to revolutionizing how medical and public health researchers collect health information through the internet and mobile technology. And today she's going to share her thoughts on using data to advance the science of health disparities. Rumi, the floor is yours.
Thank you, Emilio. And Just checking you can hear me and see my screen. All right. Okay, good.
That's great.
Yeah, and I really enjoyed hearing the other talks. And it was, great panel so far. So kudos to all the presenters. So this actually fits nicely in the order. So I'll briefly talk just about a couple of things we're looking at in terms of using data to even to understand health disparities. And so that's really relevant to the demography and sociology spaces as well. So I'll just start with the WHO definition of health equity, which you can all read it here, just to see how it's defined amongst population groups and what those bases are understood to be via. And then also health disparities, what is it? It's the metrics that we use to measure basically our progress towards health equity. And so of course, the reason this is pertinent is we see like dramatic differences in, and this is lifespan. So life expectancy by county in the United States, and you can see these massive differences where the maximum is in San Miguel County in Colorado, which has the highest around 82. And then we have some places around a lot you can see kind of in the south and the southeast below 74. And so this actually parallels some of the disparities in mortality that you have between the United States and countries in like sub-Saharan Africa as well. And then in Europe, we also see these differences. Now this is by lower administrative unit under the countries, and some of you might be more familiar with the areas and can see some of those differences as well. You can see from the legend, we're also talking about a 12-year approximate gap. And health disparities are well studied, like in the literature, and so these are understood to be related to unequal distribution of social, political, economic, and environmental resources, and they basically affect our health through different mechanisms. Most notably, we can understand that in terms of development of illness. So, for example, higher risk for getting sick. The ability to actually use healthcare, like to obtain it and utilize it, so access and cost. And then finally, health and healthcare outcomes are also going to be influenced. Okay, so one of the very understood but understudied areas of health disparities literature talks about discrimination. And I'll just outline a couple of the gaps here in the bold. Where they speak about that perceived discrimination does have a significant negative effect on mental and physical health. Basically, it's known that it gets under the skin. But what the literature also calls for is that we need much better data and methods. A lot of times discrimination is measured through proxies like census measures, like proportion of different populations, or surveys, which of course have information recall biases. So we thought we would look at online data because it's been shown as a proxy for local climate. And so you can see a few examples here from the literature, mostly at, for example, the state level in the United States, city level, where there's been basically correlations between Twitter-derived sentiment and outcomes like hate crimes, or you have some other ones like residents' racial prejudice measured from surveys, or birth outcomes. And so we know that it's a proxy for local climate. So can we leverage the online data to better understand this at the individual level is where we were looking. So the kind of model that we have, the theoretical model we have is that we have individuals with their identity, and then there might be some, and we're looking specifically at discrimination in the online world. So that could be either through one's own personal social media feed, for example, the things you see online, or you could have the online data as a proxy for local climate, like mostly like the other papers were shown. So that upper path is the one that we're using in our study. And then the idea is the pathway is that basically would cause different types of stress, acute and chronic stress, which relates to then different health behaviors and affects health outcomes. So in order to actually understand that, climate, the proxy that we're developing. This is just a little pipeline. You can see where we filtered the data to create a classifier and then made sure that that was performing well in different locations. So it's not overfit to like a certain type of speech. And then we're also able to delineate discrimination that's like a targeted discrimination or basically like a self experience of discrimination. And this is just a high level overview of the study. So there's a lot here, but basically the idea is we assess this local climate from Twitter posts, that's on the left panel. And then because the proportion, the places where people tweet is inconsistent across locations, different amounts of people will be tweeting. We create basically clusters that account for both the proportion of people tweeting and also give a more consistent representation of that local climate. We're able to do this in New York City, given the high, volume of tweets and of the spatial variance we have. So you can see that map of then those resulting clusters. And then we actually used, we had a collaborator study where they equipped a group with GPS trackers for a couple weeks around the city, and they could see, what their activity spaces are, and then we can use these locations and this climate measure to then get an area weighted measure of the discrimination exposure. So the sum of the story is that we find effects of structural discrimination. There's effect modification by race ethnicity. So you can see for folks who are white versus folks who are Black in this group, and this again is in New York City. While those two both have like a, this relationship, increasing relationship between the area weighted exposure and the number of days of poor mental health, that's different for those two groups. Like the folks in this study who are Black to have more of an effect for the maximum amount of that area weighted exposure. So that's just one example of a kind of a more full study end to end. The next thing I wanted to just show was some other things we're looking at, which relates really greatly to some of the to Rithi's talk. So I'm really glad for that, which looks at, for example, a lot of the work going on in COVID, where we had a lot of health disparities as well. And people might have heard about this in the popular press and some of the different reasons, different workplace exposures, different healthcare access, and this is data from the US, but of course this happened in different places around the world, right? So there's a lot of screenshots of the news around that, and so those disparities are also pretty well established and studied. And we thought we would look at one place where we know we've a lot of disease models, disease forecast models, is using mobility data, as our speakers nicely explained. But one thing that we can see is, as was mentioned now by this our other panelists, that the Facebook, for example, if we use Facebook data for the movement information, of course, these data represent certain populations. And although these might capture certain things, like in this case, more movement outside one census tract for places where we have more Black people versus versus just movement within the zip code. So you see like more of the correlation here as mobility increases on the left-hand side for the blue line. However, and some groups might be underrepresented. So we also see, and this is in New York again, using the Facebook ad data that was explained and the census information to get the age groups, is that we see still more correlation between more movement and more older population. So this is probably because of the folks who are on Facebook who are above 45 are more mobile than the general population. Another example of this would be, we see that the Facebook demographics just explicitly don't correlate well with the census on, for example, education levels. And so, so the next step here is then to understand how much these differences and how much this represents the population would manifest in our forecasting models that incorporate mobility information. Okay, so look forward to the discussion in the panel. Thanks.
Thank you, Rumi, for this fascinating presentation. Let's move on to the panel discussion. So for the audience and for those who sort of joined just now, I would like to make this as interactive as possible. So please feel free to put any questions or comments that you might have in the chat, or if you want to say something, just raise your hand and I will call up on you. I will catch up with the chat, but before I do that, I would like to sort of pose a general question to all the panelists. So throughout the presentations, I noticed that one sort of common theme that emerged is the importance of integrating data sources, both in terms of sort of like estimating new quantities, as well as assessing and understanding the implications of digitalization for various dimensions of life, whether gender gaps or disparities in health. And for example, in the context of public health, there's been an increasing call for considering disparities in digital access or in internet access as a social determinant of health. Now, in all sort of like these themes of integration, most of the examples that were sort of shown, with some exceptions, were sort of about integrating aggregate level data sources. We might sort of have some aggregate level data sources from one digital trace source and one other aggregate level data source from sort of more established data sources. But then integration of data can also be done at the individual level. We saw some examples, for example, in Rumi's talk and in Guanghua's talk. In particular, combination of surveys with digital data or administrative data, as well as essentially data linkage. And so I'm wondering if you think that this is the sort of the future direction. That's where we are sort of heading. For example, in demography, one area of demography that has sort of developed over time is biodemography, in which essentially biomarkers are added to surveys. So people sort of ask questions, and then they also ask people to sort of draw either a sample of something. It could be saliva or like a swab or something like that, and then additional information is added to surveys. And so I'm wondering if you think that sort of like this could also be a direction for computational and digital approaches to demography, where essentially additional information can be added to surveys as some sort of like digital markers, and whether you have seen perhaps sort of digital practices, like best practices, or essentially what your thoughts are on maybe the potentials for the future, as well as the challenges, where we're headed, and so on along the different dimensions. Let's see, maybe we can go perhaps in reverse order here. If maybe we can start with Rumi and then Ridi, Guanghua, and Andy.
Yeah, I think, yeah, it's a great question, Emilio. And I mean, you know, the forces that make it difficult for this, I mean, the challenges are, of course, we know it, you know, there's like a lot of data protection, important regulation, and that's important as well. That's going to be probably, you know, that's going to prevent people from looking at certain things. On the other hand, with, you know, there's conversation around allowing for those accesses, and, you know, a little bit, I'll just speak a little bit outside of that conversation, and at least for, you know, more on the individual level, I think we see that more on like even, you know, a lot of deeper sociological or demographic or epidemiological studies, where a lot more, like you said, information is being taken. And what is now also in the mix is that it's a lot easier for that data to be generated. I mean, I know this from acute respiratory infection surveillance. We did a lot of work on surveying, on sampling people early on, and, you know, with biological specimens, which was, you know, a very heavy lift to do several years ago. But just, you know, because of COVID, one of the things is that's become very, you know, getting tested and all that is very, very commonplace. And so I think that is going to make it somewhat easier to do that kind of data collection at scale, those kind of multiple modalities that you spoke about. So just maybe give that comment that I think pragmatically we're going to see this become, feasible.
Thank you, Romy. Ridi, would you like to add something?
Yeah, I completely agree with your sort of your speculation that forms of data integration, data linkage will be a really crucial part of the way that we do sort of digital and computational demography. And I think it already is. I think one area or one example of where it already has become data integration. I mean, there are different types of ways in which data linkage is already existing in demography, right? One is we see, for example, already survey data linked to administrative data, examples of that in a lot of European countries. We see that, we see also, I mean, in the work that, for example, I presented with the DHS, we have essentially individual level data linked to geospatial data, geospatial covariates, and that's possible to do if you have geographical coordinates in the individual level survey. So the fact that geospatial data integration to individual level data sets is happening or other forms of sensor-based measures can also be incorporated. We see evidence of that already in large-scale population surveys. So I would say that just as the biodemographic example is a really good one, I think the opportunities for geospatial data integration is also a really, really powerful way in which new kinds of research designs and questions can be asked. And I do think moving forward, other types of behavioral data could be integrated using this kind of model. One key advantage of this model is that, there's a lot of digital trace data. Also, the use of it happens in a kind of ethical gray space, right? There are open questions like what sometimes in sort of with aggregate level data sets, it's fine, but then there are, at least when we go through ethics review processes, there are lots of interesting questions asked about what kind of digital trace data should we be using when it's like publicly available, when can it be repurposed for research, when can it not? Whereas if we actually start incorporating it through a model where there is a pathway for informed consent, right? We're also creating we're kind of creating a sort of an ethical pathway also for data collection. And so I think that's a feature of this model that I think is really is promising. One challenge I see is that it's not so straightforward, even if someone decides that they want to, for example, donate their social media histories, right? How should that technically be solved? Like, it's in some cases, some companies now allow you to sort of extract all your posts or something, but there isn't always a kind of an easy way to do that from a sort of technical perspective. So there are ways. So yeah, I think it's an evolving space, but there are lots of things in its favor. And I do think that it's inevitably, there are already models for it with geospatial, with biodemographics. So I really hope that we can also think about, again, a diversity of data sets on data sources within our sort of classical sources as well.
Thank you, Ridi. Guangwa?
Yeah, so I really like this question. I will answer this in a very practical way based on my experience. So we also have the same question when we aggregate those data from different data sources. So one difficult decision we had is what's the resolution we will use? Like Professor Tatum also mentioned this in his slides. So what we, for static imageries, we can chop out in different resolutions. For road density or population, they have different resolutions in different format. So we also, another big concern is about this privacy. We want to have a high resolution, but there's privacy concerns. If it's a very high granular, there might be some compromise issue. So in the end, we decided to use a 2.4 kilometer grid cell. It's a bin tile system, and we use that system because it's a pretty common we use here for other aggregated data sets. So we can direct use and to convert all the data format to a bin tile grid cell. So it will be easier for us to clean the data and to put it into the machine learning model. So that's how we did that. Also, when we share the data about this relative wealth index publicly, the current format is a CSV file, the centroid, longitude, latitude of each bin tile, and then the relative wealth index. So that's our CSV file format. We also receive some requirement to share some data in raster format, but because that will be easier for them to resolve some issues about to convert their data set with the relative wealth index. But the issue is for the bin tile, for different latitude, the size of each tile will be different. So it will be really hard to convert from this bin tile to a raster. So we also have this issue. And I'm also curious to learn, like, what's the good format the other researchers or organizations would like to have, so we can maybe provide this data set in another format. Yeah.
Thank you, Guanghua. Maybe Andy?
Yeah, I won't add too much other than to say that, yeah, the value of the kind of individual level data is, for some of the things we've been doing, it's pretty clear in terms of when we're trying to understand why there are patterns in phenomena. So why are there children in some areas not receiving a vaccine? Why are there women who don't make use of skilled birth attendance or postnatal care? And it's only when we start to bring in the individual level data from surveys that we start to be able to describe those and understand those spatial patterns when we're capturing things like maternal education, things about the role of the woman in the household. But also on the other side of things, we have to think about how when we're producing data sets, how are they actually used? Do we need to go down to very fine spatial scales? Do we need to go down to individual level scales? We're thinking about data sets that are used for health applications. Often decisions are made at the health zone or a district level, and that sense there is we can produce a very sophisticated, very detailed sets of data, but are they actually going to be used? Unlikely. We need to be thinking and working closely with ministries of health and understanding how those decisions are being made. So there's a kind of science versus operational balance there.
Thank you, Andy. So I would like to move on, sort of following up on a question from Tom Legrand. So Tom is essentially asking a question related to partnerships. Like Tom's specific question is for Andy, and it's about partnerships with, say, national statistical offices. Essentially, like Andy, you have been showing that you have been producing excellent data that could be particularly useful. Is there a risk that some of the national statistical offices may feel marginalized and so on? And so how you approach partnerships with national statistical offices, for example. But I would say that the question is even broader, and sort of like it could be valuable for all the speakers. So for example, there are partnerships with national statistical offices, but there are also partnerships with mobile phone companies. There are partnerships with social media companies. And all of these can be addressed in different ways. I know that in the audience, we also have a number of graduate students or early career scientists. And so they would be also interested in sort of learning how can we sort of establish partnerships with mobile phone companies, with companies like Facebook, with companies like Twitter, and so on. And so I would like to sort of hear if you have any sort of thoughts or suggestions, even for graduate students. And perhaps we can sort of go in the reverse order, since this question was directly addressed to Andy. And we can start with Andy, and then Guanghua, and Ridi, and Rumi.
Yeah, it's I don't know. It's a great question, and one I could probably talk for hours on. I mean, at WorldPop, we started off very much trying to produce estimates at global scales particularly for health applications, for denominators, for health metrics, putting data out there openly and seeing it used by academics, sometimes by ministries of health, but never really in national statistics offices. So it's only really the last 5 or 10 years where we've developed a lot of active partnerships with national statistics offices. So many of those examples I showed with Afghanistan, with Colombia, Zambia, DRC are all partnerships with national statistics offices. And in this case, it's understanding what the what the needs of that statistics office is. Is there a gap and something that where geospatial support can help, and where possible, those statistics offices are producing and running the models themselves. So we have Brazil and Colombia examples recently where we have simply handed over and said, these are the possibilities, there are some models. And in each case, it's a very kind of close back and forward process of developing a bespoke model together, understanding data weaknesses, gaps, how these types of models, approaches could be used to support processes, with importantly an emphasis on not replacing traditional enumeration, but more using these digital data sources as a support to help in the collection of new data sources as an interim approach. So yeah, I think there are a growing number of examples of where the statistics offices have taken ownership and taken on these approaches. It's a long process with a lot of politics involved, and every single engagement is very different. But I think there's particularly over the past 2 or 3 years, a lot of progress in this kind of engagement.
Thank you, Andy. But perhaps we can move to Guanghua, who has sort of been both in the academic world and now in the industry, and can sort of share his experience in terms of partnerships between academia and industry.
Yeah, from the perspective of academia, so, Professor Joshua Blumenstock has lots of mobile phone data sets in different countries. I don't have that experience, but we have those data analysis. But for this industrial perspective, I really wish I have some policy manager from Meta can answer this question officially. But based on my experience, we have lots of collaborations. So for example, the population density, if I remember correctly, it's a collaboration with Colombia. And for the climate change, we also have collaborations, and social capital work is also collaboration with the academia. So yeah, there's lots of opportunities to collaborate with Meta. And besides that, we also shared lots of data set. I think in 2 channels. One is public available, like the poverty index or the social connective index in the humanitarian data exchange, that website. Everyone can download. Another data set is kind of like you can apply to be a partner. The data sets like business activity trend or climate conversation or displacement map or movement range. There are lots of partners who join this data for good at Meta already. So there's lots of data sets there.
Thank you, Guanghua. Let me see if Ridi would like to add something.
I don't know if I have anything further to add. I mean, I think, I agree with, I think one way to read, if I may sort of go back to sort of Tom's question as well, is to think a bit about, the nature of new data sources and this kind of, diversified data ecosystem, as I called it, and to think a bit about like what role do they play, right? One argument is to say that they're playing a complementary role rather than a role of substitution. And I think Andy made this point in his talk as well, that this is kind of in the intercensal period, we can think of these as complementary. So ultimately what we need both investment in sort of national statistical offices, traditional data sources, administrative data sources, but we also need to harness the potential of new kinds of data sources through transparent, open data sharing agreements that make these data possible to be used beyond just sort of, siloed settings. So ideally what we need is, open, transparent data ecosystems and data systems. And I think we need that for all types of data, not just only sort of proprietary data. So I think a very general point in response to Tom's question.
Thank you, Ridi. Rumi, would you like to add anything to this conversation?
Yeah, I mean, definitely Andy and Guangzhou have like a lot more experience working with the organizations as you described, and I appreciated Ridi's comment as well. And I would just speak to maybe another aspect of Tom's question around, we talked about this complementary nature of the data being generated, but perhaps there's also a complementary nature of the insight, right? Like the local, of how we're using the models and communicating them to local folks, as well as their insight, both on how they can use these models and then also what, towards generating them as well. And so there's probably value there that goes beyond some of maybe the more, clear-cut measurement questions that might be under their normal umbrella. So as models become more complex, how we interpret them and use them, we need to have expertise in that too. So I'll just add that also.
Thank you, Rumi. So I was going to ask Ridi to address David Lem's question, but I see that she just posted the answer in the chat. So I will skip that for a moment, but I want to make sure that all the questions from the audience in the chat are addressed. I also see a question from Ridi to Guangwa, which is about essentially how you deal with the fact that there is spatial perturbation of respondents' geographical coordinates in the DHS, how you sort of address these issues and which features emerge as the most important ones in your models. And perhaps Guangwa, you can address that question first.
Yeah, thanks for your question, Ridi. And so for this perturbation, just for a background, so the DHS tried to protect some privacy issue, they added random 5-kilometer noise for the urban areas and the 10-kilometer noise offset in the rural areas. So the location is not exactly the location for those villages. So to deal with this issue, basically for the rural areas, we find all the bean tiles within 10-kilometer areas and get their features and then aggregate them to get the average of those each of the features. For the urban areas, we also use that point as the center of radius and use the 5 kilometer as a radius to find all the tiles and then aggregate them as the feature. And then we use their RWI as the outcome to train the model. That's what we did. For the second question, I can quickly share my screen. I have these slides in my appendix. So let's see. The first point here is the connectivity features are the most important. The connectivity features is like the number of Wi-Fi's in that grid tile, the number of cell towers, and the number of mobile phone users. So that's the connectivity features, like here in the top one. And also night features also important. But for these satellite imageries, for the daytime satellite imageries, let's say there are square. If we exclude the daytime satellite imageries, the R squared doesn't decrease a lot. But if we only use set imagery, the accuracy is also like a 0.3. So the large number of set imageries collectively can contribute this model accuracy. So CNN can generate thousands of features, and then we reduce the feature to 100, and we use this 100 collectivity can increase this model performance.
Thank you, Guanghua. We are running out of time. I would have like millions of questions that I would like to discuss with all of you. And I wish we could all be in India and go out afterwards for dinner or so. But unfortunately, time is running out. But I would like to sort of make sure that we address the last question that come from the audience, which essentially, if I have to summarize, deal with integration. So on the one hand, there is integration of population research broadly defined within the broad field of computational social science, how surveys can be sort of made better in order to sort of enable us to incorporate digital information, and more broadly, like the next steps, including whether like the big questions will be sort of in the developing world, in low and middle income countries, where there's lack of data, or in the sort of rich world, where like we can do all things, but in a better way. We can sort of like reuse techniques like experiments and so on, but taking advantage of the full scale of the digital infrastructure. So this is a broad, very broad question, but I would like to sort of give you maybe like 1 minute to each of you, if you want to address these questions or add anything else that you wanted to share with the audience before we have to close at 6:30. And if there is anyone who wants to start, we can sort of follow a random order this time.
I can start, if that's okay, Emilio. Yeah,
sure,
thanks.
That's great.
Yeah, so just just based on other work and hearing a lot of the conversations, and I think it's a great question about integration, and just like kind of reading them a little bit more on the chat. Yeah, I think as actually really pointed out, the advent of a lot of digital data is in itself, you know, something that should be noted. And so what I mean is, just like really commented, and maybe myself a little bit, and actually also Guanghua in the model used information about other digital sources or information, right? And so specifically on the DHS, what it would be helpful to understand from that perspective, like the access to other digital, you know, technologies. Like I know mobile phone added, as someone just mentioned here, but like, you know, Facebook or Twitter, because a lot of that information is being used and we don't have a good denominator. Of course, we have like the ad estimates that were mentioned, and as Andy has spent so much important time doing in general for populations, how, you know, our denominators are so important. And so for gathering numerator information from these other sources, that denominator is always difficult. And not just knowing numbers in this case, but also a little bit more on the other axes, right? Like demographic axes, like age, gender, socioeconomic specifically. And that would be so good, at least from like my perspective, where we do a lot of estimation of disease burden. So not just populations, but now who has disease. If we're able to get a sense of that calibration from like this good our good standard DHS survey, that would go a lot in terms of those inferences. So just speaking very specifically to that question, because I was thinking about it recently, and maybe I'll just add as my closing remarks, was I really appreciated the range of presentations we had, and you know, I look forward to seeing that, you know, in the next few years in this field. I think it's going to have even more, you know, relevant, studies, etc., in different spaces. So yeah, thank you all.
Thank you, Rumi. So we are out of time. I don't know how how strict IUSSP is and whether they will kick us out of the room. But if they don't, I would like to give everybody like a chance to sort of in 30 seconds say something if you want to.
You still have time, no problem.
Okay, thank you, Nico.
I'm happy to go next. I just want to sort of really strongly endorse what Rumi just said, that I think one of the key challenges, and I've actually raised this point also directly also to the director of the DHS program, that I really think that it's wonderful that now starting phase 7, the DHS included questions on mobile ownership and internet use. But I really think that not just the DHS, but also in a lot of sort of large-scale population surveys, and also in, for example, censuses, I think we really need, for example, censuses don't have gender disaggregated measures on digital variables, right? They just have household level. And I think, if we really want to understand both the impacts of digitalization, but also if we want to understand, if we want to have good denominators, we really need to have more digital variables also of the self-reported type, not just on the sort of sensor, like, behavioral type in our data sets, like conventional data sets. So I think there's real value in that. And I also think on a second point that a lot of the tools of demographic analysis, sort of demographic analysis, a lot of the strengths of demographic analysis, assessments of bias, data quality, developing good, robust models, a lot of those tools can also be applied in the analysis of digital populations. And really the digital revolution has also created new populations, digital populations. So we really need to also think about digital demography as an enterprise in that direction, because it can also help us make sense of digital data streams in new generalizable ways.
Thank you, Adi.
I can go quickly with, really great points. Two things when I look to the future, it really makes my head spin, because we're having, just example of this panel, we have tech giants producing cool things. We've got demographers, we've got computer scientists, we've got, and so when we're trying to keep an eye on what might be useful for complementing traditional data sets and improving population estimates, we've got groups and space agencies mapping building heights. We've got new types of survey coming on. We've got more and more data being extracted from mobile phones. So it's a challenge of I guess training the next generation and bringing together all of these different fields so that these kinds of data can be treated in the right way and understand the biases, and not just grab a new data set and shove it into a model without understanding some of those biases. And then finally is again, not leaving behind those national statistics offices and ministries of health who may find and likely will find these kind of approaches and data sets useful. So it's working out ways to bring them along with us and showing the potential and increasing that, expanding that capacity and letting them take ownership. So it's being pulled in multiple directions, but it's exciting.
Thank you, Andy. Thank you very much. And maybe
I just have one short point to add here. So as a teammate in the Data for Good at Meta, I really want to know what we can do to provide some useful data set for the researchers. So if you have some ideas and if you have some data sets you want to know to have, let us know.
Thank you, Guangwa. So people are certainly encouraged to contact you and contact people in your group if they have ideas to share. So with this, since we're already out of time, I see that Tom, did you?
I just wanted to say that I think the session needs to end, but the Zoom room can remain open if people want to continue talking.
Yeah, so I think that So in the interest of time, and so the people may also want to go and see other sessions, which is something that I encourage you. Like if you look at the program of the International Population Conference, you will see many presentations that use new computational techniques or new types of digital data to address all sorts of issues. It's not just this panel, but you see many applications, and I certainly encourage you to sort of look at the program in detail and browse those sessions. So I would like to thank all the panelists for your excellent presentations and discussions. Thank you very much for sharing your wisdom. I learned a lot and I enjoyed this discussion very much, and I hope that everyone else did as well. And also many thanks to all the participants for their active participations, and the IUSSP for supporting the panel on digital demography. Thank you all, and I hope to see you around at the conference.
Thanks, Emilio.
Thank you.
Thank you. Bye.
Bye.
Bye, everyone.